Hello students, so I bring you this next chapter, chapter 19, where we're going to start to look at electrochemistry more in depth. We previously talked about redox reactions in the first semester, but now we'll dive more in depth about what is actually going on and how do we treat this. They'll break this down into about 3 different videos. The first one will be about just balancing the redox reactions and understanding what's going on and how it actually starts to work. Then we'll look at the math kind of side of it, where we look at cell potential and relate this to Gibbs free energy and equilibrium constant K. And finally, we'll look at some of the outlier situations and some real-world examples of redox in action. Let's go ahead and get started. So, electrochemistry. So, a quick reminder that redox chemistry requires both oxidation and reduction. That wherever there's electron transfer, redox is happening. And the oxidation numbers of our elements will change. So, essentially the charge state. An electron is lost from one element, it's gained by a different element. Sometimes the same element is oxidized and reduced. So 2 coppers split from a copper 1 into a copper 2 and a copper 0. So 2 different coppers, one goes up, one goes down. But there's always a redox. There's always one goes up and one goes down. There always must be a matching pair. If there's not, it cannot be redox. Remember, oxidation is loss of electrons. In most cases, that means to be more positive because they've lost something negative. But in biochemistry or in organic chemistry, when you get oxidized, you're typically thought of as gaining oxygens or losing hydrogens. So like a methane would be the fully reduced version of a hydrocarbon with carbon dioxide with 4 carbon-oxygen bonds and 0 carbon-hydrogen bonds, the fully oxidized version. Reduction, on the other hand, would be becoming more negative because we're gaining electrons. And so when you're being reduced, typically the atom is losing oxygen bonds or gaining hydrogen bonds. Now, one way to remember this is oil rig. Oxidation is loss, reduction is gain. But another one is Leo the Lion says grrr. Losing electrons is oxidation and gaining electrons is reduction. Now, a quick reminder on determining charges. Oxidation numbers of all pure elements are 0. Every compound, as long as it's made up of 2 or more elements, have different oxidation states. Oxygen is usually -2. Hydrogen is usually +1. Everything else can be determined by context, where they are in the periodic table and how they balance out. So the following reaction: zinc solid plus oxygen gas goes to zinc oxide. That zinc starts at charge 0 because it's a pure element and ends at 2+ because oxygen is 2-. So zinc must be oxidized. It is losing electrons. Oxygen must be reduced because it's gone from 0 to 2-. So now oxygen is being reduced, so zinc must be a reducing agent or reductant on oxygen. So that oxygen is reduced, so it must be doing the oxidation on zinc. We'd call oxygen an oxidizing agent or an oxidant. That the guy who gets reduced oxidizes something else, and the guy who gets oxidized reduces something else. But the tricky thing is sometimes you can have a reaction called a disproportionation, where the same element is oxidized and reduced, like the example I gave with copper. But in this case, hydrogen peroxide oxygen goes up from -1 to 0, and oxygen goes down from -1 to -2. So half of the oxygens go up, half of the oxygens go down, and so oxygen is both the oxidizing and reducing agent. Makes it a little bit tricky sometimes. Now, in order to understand these half reactions, understand these redox reactions, we need to be able to balance these redox reactions. And to better balance them and better understand them, we will split them into half reactions, an oxidation half and a reduction half. Because if you just balance it based on atoms alone, you can sometimes miss the charge changes. Your electrons may not be balanced, because just because the elements are correct doesn't mean the charges are correct. The net positive on the left must equal the net positive on the right. We cannot suddenly lose electrons into the ether. So if it's 2+ on the left, it has to be 2+ on the right. We have to have both sides balancing out. So we're going to break these down into half reactions and use electrons to balance the charge. And this way we're going to show the redox process occurring. The oxidation will of course have the electron as a product. The reduction will have electron as a reactant, because reduction is gaining electrons, oxidation is losing electrons. But once we have the two half reactions balanced, we will combine them in a way that balances the overall equation. So we're going to follow these several steps. The first step is typically breaking these down into two half reactions. Sometimes you'll have to split up a compound in order to see it better, but in this case, but sometimes when they're completely different, it'll be a lot easier. So I'm breaking down zinc into zinc 2+ and O2 into O2-. The first step is always to balance the elements. We'll worry about what this will do to the overall equation later. So zinc, there's one zinc on the left, or there's one zinc on the right. There's two oxygens on the left, there needs to be two oxygens on the right. Then we're going to balance the charge. Remember, you can only add negative electrons. So because zinc is 0, we have to add 2 electrons to the right. We cannot add positives to the left, so we add 2 electrons to the right. So 2+ and 2- adds up to 0. Since there's 2 O2- on the right, which makes it 4-, and O2 is 0, we have to add 4 electrons to the left, because we cannot add positives to the right to cancel out the 4-. So with that in mind, we now have the half reactions are balanced. All the elements are balanced, the charges are balanced. So now we need to figure out the way to combine these together so the total number of electrons are the same. So we have 2 electrons in the zinc reaction and 4 electrons in the oxygen reaction. So basically the only way to combine this is by having 4 electrons lost and 4 electrons gained. So that means we have to double our zinc reaction. So we'd have 2 zinc goes to 2 zinc 2+ and 4 electrons. When we recombine those, that's where we get 2 zinc plus oxygen gives you 2 zinc oxide. The 4 electrons lost cancels the 4 electrons gained, and so those drop out. If you've done this right, the electrons should drop out. So in general, step 1, if you just tried to balance this first reaction, this top reaction, you'd look, oh, it's balanced. There's 1 tin, there's 1 tin. There's 1 iron, there's 1 iron. It's balanced. But if you looked at the charge, the total charge on the left is 5. The total charge on the right is 6. The easiest way to balance this is to split them into half reactions. So we split them into half reactions, which we do. Tin 2 and tin 4. Iron 3 and iron 2. Now if we look, the atoms are balanced. Okay, that's very easy. Now, I need the charges to be balanced. Well, 2 to 4 means there's a 2 electron loss. So I need to add 2 electrons to tin 4. 3 to 2, there's a 1 electron loss. So we need to add 1 electron to iron 3. Now with that in mind, the greatest common factor between the two is 2. So we double the iron so that it has 2 electrons lost and 2 electrons in. 2 iron 3 pluses and 2 electrons gained goes to 2 iron 2 pluses. And then when we combine them together, there we go. The 2 electrons drop out. Nothing else cancels. Now the total charge is 2 plus 3, which is 8. And then we have 4 plus 2, which is 8. The charges are balanced on both sides. Now, not all of them are going to be so easy. Some of these guys are going to include oxygens and hydrogens. And so we're going to, since most of these reactions are going to be aqueous, we are going to add in water and acid or base in order to balance the hydrogens or oxygens. If you're trying to follow in the book, this is a slightly different method, but trust me, this is about as easy as I can make it. Follow these 7 steps and you won't go wrong. So step 1, split the reactions into oxidation and reduction half reactions. That's what we've been doing. Balance any non-hydrogen and non-oxygen elements by just multiplying by 2 or 3 or whatever. Putting the coefficients so that if there's a duplicated element on one side, it's balanced out on the other side. Now, for every oxygen that is present in excess on one side, we're going to add water as H2O to balance out the oxygens. Now, oftentimes, this is going to throw the hydrogens out of balance. That is okay, because we will make that up the next step. The next step is then you're going to counterbalance. You're going to counterbalance your thing with hydrogen plus protons to the other side. So as we add protons to the other side, we're going to balance out all the hydrogens we've just added through water and then some. Now that we've added protons, we've added a bunch of charges. So now finally we can balance the charges by adding electrons. The book would have you figuring out the oxidation states of each element and then balancing the charges first. My method right here, you do not need to actually know the oxidation states of your elements to balance them. Because if you know all the positives and all the negatives, you can add them up and make both sides equal by adding electrons. The step 6 is just like in the easy thing, where you're going to combine these half reactions in a way that the electrons cancel out. So we need to multiply the half reactions by the greatest common factor so that the number of electrons on the left is going to be equal to the number of electrons on the right. And then finally, because there might be a bunch of waters on both sides of the reaction or a bunch of protons on both sides of the reaction, we're going to cancel out any excess waters or hydrogens on both sides. That's going to simplify our equation way down, and that's how we're going to come up with a balanced redox reaction. So I'm going to go ahead and just do this one. I have all the work here, but I'm going to show it breaking down step by step on the document camera. So Mn2 plus and CO2 in acid. So with that in mind, let's look. So there's our, we want to balance this. This is a little tricky. 3 minus here, 2 plus there. We're going to split this into half reaction 1. MnO4 minus goes to Mn2 plus. I'm going to go through one whole half reaction at a time. So Mn, 1 Mn, 1 Mn. I could easily balance the charges with electrons, but this is going to lose far more than just 3 electrons. And so we got to figure this out. So step 2 is we're going to add oxygen. So there's 4 oxygens on the left, so there needs to be 4 waters on the right. 4 oxygens, 4 oxygens. Now 4 times 2 is 8 hydrogens. There's 8 hydrogens on the right, so I need to add in 8 hydrogens on the left. Now, the total charge is +1, -1. It's +7. This is +2. So, +7, +2. The difference in charges is 5 plus. 5 plus, so I have to add 5 electrons to the left. And that will balance this out. 5 electrons. So this half reaction is balanced. That's because this guy is 7 plus, this guy is 2 plus. We are losing 5 electrons to get to there. But once again, you do not need to know that to do this. I'm just balancing the charges. If I tried to balance this, the electrons first or anything like that, I would have had 3 electrons on this side and not 5 electrons on that side. So the next half reaction, C2O4, 2 minus, CO2. Step 1, balance the non-oxygen elements. 2 carbons, 2 carbons. Okay. 4 oxygens, 2 times 2, 4 oxygens. Okay. So I don't need to add water. I just need to add electrons. 2 minus, 0, so I have to add 2 minus. It's balanced. Okay, with that in mind. The greatest common factor between 2 and 5 is 10. So this whole thing needs to be multiplied by 2, and this whole thing needs to be multiplied by 5. So when all's said and done, we have 16H plus and 2 MnO4 minus plus 5 C2O4 2 minus goes to 2 Mn2 plus and 8 water and 10 CO2. There's my balanced chemical reaction. I mean, technically I could make this as 2H MnO4 and 5H2C2O4. That's still going to leave 4 additional protons. And so we don't need to make this more complicated than it already is. Now, the next part of the slide says, what about if I ask for basic? What if I ask this to be done in basic conditions? Basic conditions are a little bit harder because a base is thought of as an OH. So every time you're adding an OH, you're adding an oxygen and a hydrogen. So when you're adding an OH, you're adding one less hydrogen than the water. And so you have to carefully balance this. But one easy way to balance this, the one way to think of it is I add 16 OHs to both sides. Every OH cancels an H to make 16 waters. Well, there's 8 waters on the left, cancels with 8 of those 16 waters on the, well, there's 16 waters on the left and 8 waters on the right. They cancel with 8 waters. And so you're left with 8 waters on the left and 16 hydroxides on the right. The net effect always is, when you turn it basic, is we're swapping places. The water goes to the left, the water switches side, and the protons switch side, but the protons become hydroxides, and it will balance its way out in the long run. So when you are asked to balance in base, I still say balance this in acid and then swap it to base. It will be much easier to work with. Much easier to work with. So, as I said, just we're going to swap places. Essentially, the H's turn to OH's, and the OH's and water swap side. So 8 water, 2 permanganates, 5 oxalates, go to 2 manganese 2 pluses, 16 OHs, and 10 CO2s. Obviously, we need to keep practicing. Because these are not easy, and so we need to keep looking at them. H2O2, so hydrogen peroxide and chromium 3 goes to water and dichromate in acid. Okay, I wrote that half reaction down so that we can now look at this. Okay, 2 half reactions. Let's do chromium first. Chromium 3 plus dichromate. 2 chromiums. Okay, that's step 1 and 2. Step 3, well, we have 7 oxygens on the right, so we need 7 waters on the left. 7 waters. That means we're going to have 14 hydrogens on the left, so we add 14 hydrogens on the right. So 7 times 2 is 14. The total charge on the left is 6. The total charge on the right is 12. So we have to add 6 electrons to the right. This half reaction is balanced. second half reaction. H2O2 goes to H2O. So we're going to add another water. Okay. 2 oxygens, 2 oxygens. 4 hydrogens, 2 hydrogens, so we need 2 H pluses. Charge of 0, charge of 2 plus. We need to add 2 electrons here. So, greatest common factor between 6 and 2 is 6. So we're going to multiply this reaction by 3. And this one doesn't need to be multiplied at all. So we have 7 waters and 2 chromiums and 6 protons and 3 peroxides. Goes to dichromate, 14 hydrogens, and 6 waters. I've already pre-canceled out my my electrons. Now, here's the thing. We cancel out all things that appear on both sides. 6 waters cancels out with 6 out of the 7 waters. 6 protons cancels out with 6 out of the 14 protons. So my equation is actually simplified into this. 2 chromium, 3 pluses, and 3 peroxides goes to dichromate and 8 protons. Holy cow. We've lost our water from the right side. We lost our source of oxygen. So where is the oxygen going to? Well, the oxygen from the peroxide is going into the dichromate. So it all works out in the end. Because let's look. 3 times, so 2 chromiums, 2 chromiums. 3 times 2, 6, plus 1, 7 oxygens. 6, 7, 8 hydrogens, 8 hydrogens. Total charge, 6 plus, 2 minus, and 8 plus is 6 plus. Everything is balanced. It may be a weird situation, but it is fully balanced. So that is our net reaction there. Let's do one more, another weird one. HO2 minus, that's a peroxyanion, and H sulfurous acid goes to OH minus and HSO4 minus in basic conditions. Basic conditions. Let's do the sulfurous reaction first. H2SO3 goes to HSO4 minus. S1S. 3 oxygens, 4 oxygens. I'm going to add water. 4 hydrogens, 1 hydrogen, so we're going to add 3 hydrogens. And we have 0 charge on this side. We have 2 positive on the right side, so I have to add 2 electrons. Now, if I want to, I can make this basic right now, or I can make it basic later. Let's look at the other half reaction first. HO2 minus. We're going to have OH minus. Well, we can add, you can do this one of 2 ways. You could add water, or you can try to balance the oxygens. Let's go ahead and try to do it with water. Let's put water on this side to balance the oxygens. 2 oxygens, 2 oxygens. Now we have 3 hydrogens, 1 hydrogen, so let's put 2 hydrogens. We have 2 plus and we have 1 minus, so we have to, actually 1 plus and 1 minus. So I need to add 2 electrons here. Let's go ahead and make this basic. So we're going to flip the, let's make both of them basic. We could try combining them. No, we'll combine them now. We'll combine them now like they are. So we have water cancels water. 2 protons cancels 1 proton. And so when all is said and done, this becomes, okay, we have H2SO3 and HO2 minus, so HSO4 minus, and H plus and OH minus. Well, we can simply combine those together to form water. Form those together. So we have 3, 4, 5 oxygens, 4, 5 oxygens, 2, 3 hydrogens, 1, 2, 3 hydrogens, 1 sulfur, 1 sulfur, 1 minus, 1 minus. That's our net reaction. It's kind of a little weird one, but it works its way out. We don't actually see this being basic, even though it is under basic conditions. Okay, that is where I'm going to stop this first video. Following this, we are going to look at cell potentials, but that will come in the next video.